Structure contours are a powerful tool for describing the three-dimensional geometry of geological surfaces, like the boundary between different sedimentary formations, or an unconformity surface, a fault plane, or even the sides of an igneous intrusion. All are surfaces in 3D space, just like the Earth's landscape is a surface in 3 dimensions that separates the solid Earth from the atmosphere. We describe the geometry of the landscape using topographic contours, which give us an idea of the slopes of hillsides and their orientation. And we use structure contours in the same way. They are on the geological feature rather than the Earth's landscape, and their trend tells us the strike of the surface, and the spacing of the contours gives us an idea of the dip. So let's illustrate structure contours using this rather crude clay model, and we've embedded a piece of blue sponge which represents a geological layer, and the strike of this geological surface, which is the top of the sponge, is picked out by that cane. Right, well, let's encase this layer back in the ground and put the rest of the landscape back on top. So here we have the blue sponge, the geological formation, going down into the subsurface. And the way the model's set up is that there's a valley running through the system like this. Okay, so now let's just look down on the model as though it was a map. Here we go, we're looking down on the model and you can see the valley running through the middle of the image and the blue sponge running around. So let's just add in some topographic contours. Let's say it's the 100-meter topographic contour. And the geological boundary intersects that topographic contour in 2 places on either side of the valley. And if we join those up, we're connecting points of equal elevation, not only in the landscape, but also on the geological surface at the top of the blue sponge. And this contour of equal elevation on the top of the blue sponge continues beneath the clay, as shown there. So this is a structure contour, and if that was a pick at 100 meters, because that was the elevation of the topographic contour, that's a structure contour on the top of the blue sponge at an elevation of 100 meters. Well, let's look down on this sponge again. Here we are, so we're looking down on our blue sponge with some structure contours drawn on, and the one we've been looking at, we joined up these 2 points of equal elevation on the landscape, where the boundary of the top of the blue sponge comes up to the landscape, and we join these up to make a continuous structure contour on the top of our blue sponge layer. And there's an array of other contours that we could draw, equally spaced, running down the dip of the blue sponge. And of course, this blue sponge layer existed with a greater extent. It extended into what is now above ground. So let's again strip off the landscape, and here is the extent of our blue sponge with our structure contour shown in the red bar running across there. So this is our illustration of the structure of the planar surface that is the top of our blue sponge. This is for a planar boundary, that surface is a plane. And for a planar geological surface, the top of our blue sponge in here, the contours are parallel and straight and equally spaced. The trend of these straight lines is the strike, and the spacing between different contours gives us an idea of the gradient of that surface, in other words, the dip. So let's use these methods to interpret a couple of geological maps. And we'll start with this one. So here's a classic structure contour problem. It's a map with the north arrow and a scale, and it's also got topographic contours which are in meters, running from 80 meters here up to 110 meters. You can see that there's a valley down in here where the low ground is, and 2 hills on either side. And what we're going to do is draw structure contours on this feature running through here, this geological layer, using the map pattern, in other words, how this layer interacts with the topography. Our mission is to estimate the depth to this layer in this borehole. So let's walk along this boundary and find the intercepts of it with some topographic contours. We're going to look for the contour elevation that intersects this horizon the most times. So 110 intersects once, twice, 3, 4 times. The other topographic intersections are only twice. So the most constrained structure contour is going to be at an elevation of 110. So let's just mark out these places. There's one there, there's one there, there's one there, and there's one there. So 4 places where this geological boundary is at an elevation at outcrop at 110 metres. Well, I can see that these all line up onto a near perfect straight line, which means that the boundary has a near constant strike for this area. And so we can join these up as a straight line. I'm nevertheless going to just freehand it in because I don't want to imply that it's necessarily perfectly straight. So this is the structure contour of value 110 metres. And it's worth labelling it up as you go. Okay, so we know an orientation for the structure contour of value 110 metres. Now let's put in some other structure contours. And if this surface is perfectly planar, the other contours will be parallel to the one we've drawn already. So let's confront this by looking down here at the 80 metre intersection of topography with the boundary. And it intersects there and there. And if we join those up, they can only join as a straight line, there's only 2 points, we can see that the structure contour of 80 metres picked out by that cane is parallel to the one that we've constructed already for 110, confirming this idea that the boundary is dipping this way from 110 high ground down to 80 metres low and is planar. So let's just construct the 80 metre structure contour, which is going to come through here like that, and we can now extrapolate it out in this direction, which I'll just do along this straight trend in here. So that is our extrapolation of the 80 metre structure contour running across the map like this. Okay, so there are more structure contours we can draw because we have the intercept of the 90 metre topographic contour and the 100 metre topographic contour with the boundary, which allow us to draw 2 more structure contours. These, if this surface is perfectly planar, these contour intervals should be equally spaced on the map. So let's see how we do with that. Here's the 90, and just draw that in. I'll just draw it across this area first to make sure that it's working okay. So that's the 90 metre. And here is the 100 metre, which we can just draw in across here. And we can see that these are indeed equally spaced within the drafting error that we've had to live with. So it's a planar surface as far as the data that we've got here can tell. So we can use this now simply to project with some confidence the other 2 structure contours. There's the 100 and here is the 90 projected out across the map. So let's now estimate the depth to this geological surface in here in the borehole. So let's just cartoon up what we're doing. Here's the land surface, here's the borehole, here is our boundary dipping south. So this would be north-south in our cartoon. And the question is, what's this depth? So first of all, what's the elevation here? Well, let's say it's about, there's 110, there's 100. So let's imagine that it's something like, about 103 metres. It's a little bit closer to the 100 than the 110. So let's say that's 103 metres elevation. And in the borehole down in here at the bottom, the boundary would be somewhere between the 90 metre contour and the 100 metre contour. Sorry, between the 80 metre contour and the 100 metre contour. It's closer, if anything, to the 80 metres. So let's say it's down at 83 metres here. So that is our borehole setup, and the difference between these 2 is clearly what? 20 metres. So that is the depth in our borehole to intersect that horizon. That's how deep we have to drill down to intersect the horizon. Finally, we can estimate the orientation of this boundary with a strike and a dip. Well, the strike is the trend of the structure contours. They're otherwise known as strike lines. And you can see from the relationship to the north arrow that the strike is 090. And the dip direction goes from 110 to 80 southwards, shallow level going deeper this way, so therefore it's dipping south. To find out what the dip is, we have to use some trigonometry. Okay, so in order to do this, we're just going to measure the separation between the 80 and 110 metre contour. We're using the maximum information we've got. So that distance there, over that distance there, the elevation of our boundary has changed from 110 down to 80 metres. So we need to work out what that horizontal distance over which that vertical change has occurred. Notice that I've measured perpendicular to the trend of the strike lines. So let's see what that distance is. Put it onto the horizontal scale. That's 100, and the residue on that is what? About one, that's about halfway, isn't it? So that distance is 150 metres. So let's take this information and draw up our trigonometry. What we're saying is that the surface is going down like this. It changes elevation from 110 to 80, so that's 30 metres elevation change over a distance of 150 metres. And so the angle in here, alpha, which is the dip, alpha, or the tangent of alpha, is going to equal 30 over 150, which is 1 over 5 equals 0.2. So we now just have to look up and see what the inverse tan of 0.2 is. And the answer is 11 degrees. Okay, so we can now take this and put it onto here. The dip is 11 degrees south. So a simple structure contour exercise to establish the depth of a horizon in the subsurface and its orientation as a strike and a dip. So in this structure contour exercise, we'll use the map pattern over here and use structure contours to extrapolate this boundary into this area here. Okay, so let's just zoom in on this complete map. And we'll start by picking the 110 contour here, 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 and here. 4 places along the same topographic contour intersection with the structure contour. And we can join these up through here like this. I'm going to use a ruler for this for reasons that we'll see in a minute. Okay, so these line a straight line, which means that we can project this structure contour now out across the rest of the map. Let's build the rest of the array. We'll just label that before we go. That's 110 metres. Okay, and I can see there's a 100 metre intercept there and there. And again, let's just join this one up. We can see that it's parallel to the 110 contour. Like that, to label that 100. That's 100. Because that's where the topographic contour of 100 coincides with the boundary. And let's put on the 90 metre here and here. Again, let's join that up as a straight line. Like that, so that's the 90 metre. And then finally, we can put on the 80 metre structure contour down here, which is the last intercept of the topographic contour system with the geological boundary. So there's our structure contour array for this part of the map, with the intercepts of the topographic contour with a geological boundary. Let's just zoom out. Right, so now we're just going to project these structure contours from the map here out into this unmapped area. And let's just do these in turn so we know what we're doing. So here is the 110 contour, and we're extrapolating it from our known array out over here like this. And now we can find places along it where the 110 structure contour intersects the topographic contour. Here and here. We'll use that shortly. Let's do the same with the other structure contour. So we can extrapolate out the 100 metre structure contour, which I've marked in red, like this. And we just extrapolate this out over here, across the map. And this intersects the 100 metre topographic contour here, and here, and here. So 3 picks. Oh, there's one there. 4 picks on the 100 metre topographic contour with the structure contour. Continuing, let's put the 90 metre contour on now. Here we go. Let's hold this still. 90 metre out across here like that. So that's the 90 metre structure contour, and it intersects the topographic contour here and here. And now we can just put the 80 metre structure contour on to complete the array, or at least that part of the array that we've mapped up so far. And we can see that this intersects the topographic contour of 80 metres here and here. So we've got an array of picks in here where the boundary is predicted to intersect the topographic contour where it has the same value as the structure contour. So what we need to do now is simply join these up. So the boundary is going to come down here like this, intersect that point, and it's V'ing into the valley and then up the other side like this. Now, I'm not going to keep drawing it for a reason that will be obvious in a minute, because it's hard to see where it's going to go next. Let's come here, but in this position we can see that the boundary comes down this like this, V's into the valley here, and back up the other side like that. So 2 V's into 2 valleys. But what happens here? Well, to answer that, we're going to extrapolate our array of structure contours to values that extend beyond 110 metres, because we can see that these are more or less equally spaced. So we can use that spacing, and I'm just going to measure here the spacing between the 100 and 110 contour and extrapolate it up like this. So here is a point which is the 120 structure contour, and then a point over here. We'll just join those up as a straight line like this, which I'll use the black line for. I'll just dash it so we don't get confused with the boundary, which we'll draw on in a minute. So that is the inferred 120 metre structure contour. So we go 80, 90, 100, 110, inferred, projected 120 metres. So in the same way as we did for these other structure contours, where does the 120 metre structure contour intersect the topographic contour of the same value? 120, one there and there. So our geological boundary is going to come up like this. It cannot cross the 120 contour, topographic contour again, unless there's a intersection with the 120 structure contour, and it can't cut the 130 topographic contour unless there's a 130 structure contour there. So it has to lie between these 2 topographic contours like that. So there, and I'll just go over it, there is our geological boundary projected into a previously unmapped region using the pattern in the mapped area over here to project the structure contour array and hence forecast where the geological boundary exists. So a couple of simple illustrations of using structure contours to forecast the geometry of a planar geological surface.